Hi there, everyone. This is Tasib Ahmed. I'm currently studying in London South Bank University. So today we will try to discuss about partial differentiation. There are two types of differentiation, which is ordinary differentiation, and the other one is partial differentiation. So the question is why we need to do it partially. It tells you how one variable affects a system when so many variables are included in a system. As for ordinary differentiation, we try to differentiate according to only one variable. There are no second variable included. But in our real world, there are so many systems which are dependent on multiple variables. So we try to differentiate with one variable to see how the outcome will be while keeping the other variables constant. If we take an example of a temperature distribution on a flat floor, so as the flat floor is a 2D dimension, there is an x plane and there is another plane which is y, and it's a scalar quantity, so there will be only number, there will be no direction for temperature, and it will be dependent on two independent variables. There is the equation for a scalar field, which is x squared minus 2y squared. For the location where x equals 0, x equals 0 and y equals 0, we can get the temperature quantity, which is 0. And for x equals 1 and y equals 0, we will get the temperature value, which is 1. So for different location, we get the different values for temperature. On the other hand, there will be a velocity distribution, which is a vector field, because velocity is a vector quantity. So there will be a direction and there will be a number, and which will be dependent on two independent variables, which are x comma y. So if we take a deep look for a scalar field, which will look like a surface contours, and we want to measure how temperature changes for two different planes, and as t is a real single value, we try to keep it like delta t over delta x. So if we differentiate according to x variable, it will be written as delta t over delta x, where y will be constant. And on the other hand, if we try to differentiate with y variable, the x will be constant. So the first one here, for temperature scalar field, x squared plus y squared. And if we differentiate the temperature scalar field with respect to x, the x squared will become 2x. And for y squared, there is no x part in it, so it will become 0. So the whole thing will become 2x. And as for differentiation according to y variable, the x squared part will become 0 and y squared will become 2. So it will become 2y. So here is another example where e to the power x will become e to the power x for with respect to x differentiation, and sine y will become 0. There's no x part in it. On the other hand, though, for delta t over delta y, e to the power x will become 0 and sine y will become cos y. And here is another example of a scalar field where e to the power x times y squared. Here now we have to use UV rule, where for the first time, we keep u as a constant and we will differentiate v, plus we will keep v constant and we will differentiate u. So if we try to do it with respect to x, e to the power x will become constant and y squared will become 0 as there is no x in it. And we will keep y squared as a constant and either try to differentiate e to the power x, which will become e to the power x. So it will become e to the power x y squared. On the other hand, delta t over delta y, the whole term e to the power x y squared will become 2e to the power x y. For the fourth example, is quite difficult because there is a chain rule where we will try to differentiate x minus y. We will take it as u, and y minus 2 whole cube will take it as v. So we'll keep u x minus 1 whole to the power 10, and we will differentiate v y minus 2 whole cube according to x. And there is no x in y minus 2 whole cube, so it will become 0. And for the next part, where is y, x minus 1 whole to the power 10 will become 0 because there is no y part in it. As you can see, y minus 2 whole cube times x minus 1 whole to the power 10 differentiation according to y, and it will become 0. So for delta t over delta y, the final term will become 3 into x minus 1 whole to the power 10 y minus 2 whole square. So now there is a scalar field where the temperature is dependent on 3 independent variables, which is x, y, t. T represents time. And here is a equation for this, which is x minus 2 whole square plus y minus 2 whole square times 2t squared plus 1. So now UV rule will come again. So if we differentiate the whole equation according to x, the y and t will become constant. Now you can see the third term t, which represents time, the y and time will become constant. So if we differentiate the whole equation, the 2t squared plus 1 will become 0 because there is no x in it. And if we differentiate the first part, the x minus 2 whole square will become 2 into x minus 2, and this part will become 0. So the whole thing will be 2 into x minus 2 times 2t squared plus 1. As for y, we will keep x and t constant. So for t squared plus 1, there is no y in it. It will become 0. And we will keep the first term as constant. And for v, delta t over delta t over delta small t, we will keep x and y constant, where we will keep u, which is x minus 2 whole square plus y minus 2 whole square, as constant, and there is xt in it, so we will have to differentiate. It will not become 0. So 2t squared will become 4t, and plus 1, the differentiation of 1 is 0. And for v, 2t squared plus 1 will become constant, and we will differentiate the first part according to small t, and it will become 0 because there is no t part in the first term. So it will become 4t times x minus 2 whole square plus y minus 2 whole square. So here is another example of a scalar field which is dependent on 3 independent variables. So as for this function, we will try to differentiate according to x, y, and z. For x, we will keep y and z constant, and the whole thing will become 4x minus yz. For 2x squared, it will become 4x, xyz, there is x in it, so it will become minus yz, and for y squared z, there is no x in it, so it will become 0. So now we will come to our final example where a function which represents a scalar field dependent on three independent variables, and the equation is z e to the power x y. So we need to find out the double derivative of the function. So to find out the double partial derivative, we need to find out the first order partial derivative. So where for x, we will keep y and z constant, and it will become y z e to the power xy. And as for y, we will keep z constant and e to the power xy. It will become xz e to the power xy. And as for z, e to the power xy will become constant, and we will differentiate z, which will become 1. So eventually it will become e to the power xy. So as for second derivative, we will take the part we got from first order derivatives. Here we will try to do for the second time according to x, y, and z. So for the x, we got yz e to the power xy, and here y will come to the front. It will become y squared z e to the power xy. And if we differentiate according to y, the x will come to the front and it will become x squared z e to the power xy. And for z e to the power x, we got e to the power xy from the first derivative, and there is no z part in it, so the differentiation will become 0 as we take it as a constant. So finally, we have to find out delta square f over delta x and delta y. So here z will be constant. As we can see, z will come out of the equation, and we will try to differentiate according to delta x, where x e to the power xy. So here uv will come out, where we will keep e to the power xy constant, and we will try to differentiate it according to delta x, and it will become 1. And for the next part, we will keep x as a constant, and we will differentiate e to the power xy according to x. So then y will come out as a constant, and the differentiation of e to the power xy will become e to the power xy. So finally, we already got the term, which is z to the power xy times 1 plus xy. Thank you guys for watching. We'll see you later.